let me just, okay, so that's a kind of my, okay, I can now go this, okay. Okay, so we have, wait 1 minute and. Okay, shall I start or?
Yes, please. When you're ready.
No, let us wait, maybe we'll, okay.
Yeah, well, it's up to you for a couple of minutes, yes.
Okay, let us wait a couple of minutes. I still have a time for a coffee. So probably I can start on.
Yeah, just a moment. I'm just admitting people. Some more people are coming. So it's my pleasure to have with us Nikolai Leonenko, who will talk about multifractal processes. Please, Nikolai.
Okay, thank you, Elena, for invitation to give a talk, and hello, ladies and gentlemen. So I decided to present in the first part of my lecture kind of introduction to multifractal processes, and then maybe to the end I will present some new results. So basically my idea to invite you to a beautiful world of multifractal analysis, but of course it's only introduction and only one lecture because I'm busy with other commitments today. And again, so what is important to emphasize that there's no unique approach or definition of multifractal processes. Basically, there are models, and for each model, we have to prove some property which could be considered as multifractal property. And well, we have to mention probably the classical paper of Mandelbrot, which first introduced so-called multifractal cascades. I will not consider this example. It is probably even in Wikipedia, but again, basically, there is no unique, in my view, there is no unique definition or even unique approach how to characterize multifractality. So I will mention 3 of possible approaches, and one is probably very close to most of you know, and this is so-called, it's related to self-similarity. Probably know that there are self-similar processes, and this processes looks like suppose that process xt is self-similar if finite dimensional distribution of a process is x of ct, that's equality of finite dimensional distribution is equal to c to the power h x of t. So instead of m of c, we have to put to imagine c to the power h. H is some sort of parameter of self-similarity, sometimes called Hurst parameter. And basically, in this definition, the first definition, you can see that multifractality is simply generalization of self-similarity. So a stochastic process x of t is said to be multifractal if finite dimensional distributions of process x of ct is equal to m of c times x of t. So now instead of this c to the power h, which we usually know from definition of self-similar processes, m, that's true for every c, and mc is a random variable independent of x of t, and whose distribution doesn't depend on t. So basically, instead of kind of non-random multiple c to the power h, we have here some sort of random variable. And this random variable usually has a scaling property. I mean that if you consider m of a times b in distribution, this is m1 of a times m2 of b for each a of b, when m1 and m2 are independent copies of m. So basically, even from this definition, you can see that multifractal property is kind of more about product of random variables than for us about sums. So this is true, and we will confirm this in the future. So what is the second definition? The second definition is the following. It's could be called definition by using moment scaling. Before to go to this definition, let me emphasize that if x of t is h self-similar process, for instance, could be fractional Brownian motion, in this case, h between 0 and 1, and then for a finite moment of order q, it's easy to show that expected value of x of t to the power q is expected value of x of 1 to the power q and t to the power hq for all t. And from the above definition 1 and 2 properties, it's easy to see that it's not a proof, but kind of idea of proof that expectation of x of t to the power q is expectation of x of t to the power q time expectation of m of t to the power q. You remember that m is independent of x. And then this is expectation of x of t to the power q and t to the power 2 of q. So in this case, this moment of this random variable, well, maybe it depends on t, is a function of q. And again, if you compare this self-similarity, we can see that this is basically a generalization of self-similarity, because if self-similar case, this function tau of q is simply a linear function, and it is equal h times q. H is first parameter and q is order of moment. So basically, you can see that from this definition, which can be called through scaling of moments, yes, if property of a process such as we have a scaling of moment but function in contrast to self-similarity is non-linear, that's a feature of multifractality. I will give precise definition a little bit later. And that's the second definition of multifractality. The stochastic process is said to be multifractal if there is a functions c of q and tau of q such that increments, expectation of increments of x of t minus x of s to the power q is equal to c of q, t minus s to the power tau of q. And usually it called for some q, q is not arbitrary, q usually belongs to some special set. And t and q are intervals on the real line which positive lengths. And basically, if process has definite increments, then expectation of x of t to the power q is c of q times t to the power tau of q. That's exactly we saw this definition. And if tau of q is q times h, that's a property of, let's say, of self-similar processes. So this function tau is called scaling function. And it's possible to prove its general property, which is there are many properties, but is concave. And of course, as I said, if a process is self-similar, tau must be linear. Okay, a couple of examples. First example, which are known again in the literature. The first example is known as log normal cascade, LNC. So theta of t with intermittency parameter lambda square is a process such that that's a non-negative, non-decreasing with stationary increments, and for c between 0 and 1, finite dimensional distribution of a process theta of ct is equal to theta of t, and this random variable is now specified. This is c e to the power 2 gamma of c, and gamma of c has a normal distribution with mean lambda squared log of c and minus lambda squared log of c independent. We know that this function, this random variables must be independent of a process theta of t. So again, this is simply the same as we already saw in our first definition. The only thing that we now specify is this random variable, which has an exponential form. And of course, the second property follows because of exponent has a property that product is exactly what we need. So it's possible to prove that for a q from minus infinity to 1 over 2 lambda square, this scaling function in this case is equal to q 1 plus 2 lambda squared in this notation minus 2 lambda squared q squared. So this is simply quadratic parabola. And again, it's important to emphasize that in multifractal analysis, negative Q are also very important. So basically, usually Q, it's very difficult to prove that it's called, very rare, but exists such a situation when Q belongs to real line, but usually Q belongs to some special sets, and these sets, this set must contains, well, not must, but it's better if it contains negative values, because for negative values you have very specific property which is important for application. So basically, again, well, in our examples, which are Q will be positive, but again, if it's possible, it's better to include also negative moments in this consideration. So the second example is log normal multifractal random walk, so-called LMMRV. So in this case, process defined as follows. X of t is a Brownian motion in which we use a time change. And instead of time, we use a theta of t, which is already log normal cascade, which we already introduced. So, and in that case, x has a stationary increments, and in finite dimensional distribution, x of ct is equal to this property, as we know. And basically, again, this is what we already know, that gamma is index c, has a normal distribution with some special mean and special variance. And again, in this case, if q from -1 to 1 over lambda square, yes, expectation of x of t to the power q is finite, and this scaling function tau of q for this log normal multifractal random walk is equal to q half plus lambda square minus lambda square over q square. Again, this is quadratic function. This is quadratic function, but not linear. Okay, for self-similar processes, functions already must be linear. And the third approach, which I would like to mention, is came from the known theory of from analysis, basically. Because of many functions, forget about stochastic processes. Suppose that we have just a function, and Hölder continuity in point means that function maps 0 infinity into R, for instance, and this is C gamma at points t0 if there is a constant c such that for all t in some neighborhood of theta, f of t minus f of t0 is less than c t minus t0 to the power gamma. So basically, idea of multifractal function that Hölderity or Hölder parameter depends on the point. It could be one Hölder parameter for some function, but for some special functions, Hölderity depends on the point. And again, pointwise Hölder exponent at t0 of f is defined as supremum of gamma such that f belongs to c gamma of t0 as we defined. And if we define the set c of h such that h of t, which is defined above, is equal to h, then spectrum of singularity or multifractal spectrum is defined as Hausdorff dimension of this set ch with some conventions. And in this case, so many functions, you know, from analysis, classical functions like Weierstrass function, Riemann function, Weyl function, all these strange functions which are very important for analysis, they are multifractal basically. There are some paper by Jaffart about this. Again, there are some direction to multifractality without stochasticity, without stochastic processes. There are some functions, and we have to prove multifractal properly. It means that that's an exact definition, but basically it means that at each point, Hölderity of the functions depend on this point. It's not a, it's kind of close to the what Julia Michaud likes to call multifractionality, but multifractality is a little bit different. And regarding to stochastic processes, yes, the function is multifractal if its spectrum is non-trivial. So not a one-point set. That's a spectrum of singularity, so-called. And definition of stochastic process is now stochastic process on some probability space is said to have multifractal paths if for almost every omega from space of elementary events maps t to the x t of m is multifractal function. So this is a third definition which we considered. And as you see, this definition is quite different. And basically, for each model, we have to prove one of it, or the equivalent could be, or I mean, there is no. With one of my PhD student, Daniel Grahovac, we try to collect from the literature all possible definition and all possible examples. This paper is published in Fractals, and I mentioned this paper in literature, but again, there is no, we were convinced that there is no kind of unique view on this subject. For each model, we have to prove that these three definitions are equivalent, or maybe only one definition works, or whatever. Okay, so fractional Brownian motion is, I'm sure that already considered in this series lectures. I will not repeat here definition. And in this case, this function which we introduce is equal to 1 if h is equal to h and minus infinity otherwise, which is defined. So again, multifractal paths, it's kind of very often Levy processes. And again, among Levy processes, there are some self-similar processes like alpha stable and processes and or alpha stable subordinator and inverse to subordinator. They have clear dependence and they're self-similar. Of course, we can, in this case, we have the same picture that scaling function, for instance, according to second definition, is simply linear function, is alpha over, yeah. Okay, that for many Levy processes, there is a paper of Jafart again about this. We have multifractal paths, and basically Levy process is a good example of the stochastic process. Not all, but of course not Poisson process, not Brownian motion, but many of them are good example of the Levy of the multifractal processes in according to the third definition, when sample paths are multifractal as a functions. Okay, also this is without proof, but for a log normal multifractal random network, d of h, which is defined, is equal to 1 minus h minus half minus lambda squared over 2 over 2 lambda squared, and h belongs to some specific sets, or otherwise it's infinity. So that's again feature of multifractality. So again, regarding to discussion about multifractionality and multifractality, it's a long story. Julia Mifra organized, I think, how many conferences, maybe 5, 6, I don't remember. I was invited to at least some of them. And actually, yes, I mean, what is a multifractional approach? We consider some sort of object, like some sort of representation of fraction Brownian motion, and then this h, we assume that h is a function of t as well, and it's a starting point in some representation, maybe in time domain or spectral domain. And again, in my view, this is different object, but of course there are relations somehow because of sample paths of multifractional processes as kind of satisfying main requirement for the multifractal processes. Anyway, I will present my favorite examples and theory later on. Okay, and we have to say about physicists. In physical journals like Physics A, B, C, the multifractal analysis is a kind of typical analysis. You can see if you have some data, there is a mean, there is a sample mean, there is a spectral density, whatever we use in our research, but also there is multifractal analysis. But for physics, they simply, because to prove some multifractal property is not easy task mathematically, so they usually use some sort of so-called formalism. Basically, when they can compute this function tau of q, which I called scaling function. It was our second definition. You remember that scaling function was linear for self-similar processes and non-linear for multifractal processes. Then they use kind of a Lejeune transform of this function, infimo of q, h of q minus tau of q plus 1. So this one simply means that this function tau of q plus 1 is so-called Rényi function. I will define a little bit later the function, so it's not like some misprint. It's sort of not important, of course, this one, but important that if you have a scaling function, you can formally, they usually do formally Lejeune transform, and then they call this object multifractal spectrum or spectrum of singularity. And as we know, this is kind of concave function, like quadratic function we saw in some examples. And you can see on this why physics is interesting, because they can see all objects which we know and they know as a points of this on this spectrum. So we have such a function, let's say, that called it multifractal spectrum or singularity spectrum. And for instance, for one q, this is Hausdorff dimension. For another q is box dimension. For a third q is whatever, Rényi dimension, correlation dimension. So if process is monofractal, all these points coincide. So it means that multifractal spectrum of singularity consists of 1 point. For instance, for a fractional Brownian motion, it's 1 over h. But if process is multifractal, we have a kind of not 1 point, and this is spectrum of singularity. And we can see on this spectrum of singularity many important features which physicists like. Like I mentioned some dimensions, but many others. So that is why they use this formalism, and usually they do not prove this result that basically that formalism works. And it's usually difficult mathematical part from our definition, either the first one or second one or third one, to prove that basically this is singularity spectrum or multifractal spectrum is given by this form. But again, for physicists, they use what's formalism and use it very widely. I think in half of the papers in any physical journals, you can see this picture. There is a data, and there is a scaling of the moments, and then Legendre transform, which is called multifractal spectrum. So, for instance, for a multi-applicative cascade, formalism holds. That's the first example of Mandelbrot was so-called multi-applicative cascade. I'm not going. It's kind of related to famous Cantor singular sets. We have to divide it some sets into some parts, and I'm not now going to this because it's maybe 20 minutes we need to introduce. But anyway, for this case, this formalism is completely proved. There is I could not give now a reference, but it's proved. So, I mean, there is one model which I didn't introduce here, but it's called multifractal cascade, the first model of multifractality, in which it is proven that this function is exactly given by this Legendre transform for some Q, which is related to structure of this model. So again, some distribution characteristic of the process determines the spectrum. That's basically multifractal formalism, and our task as mathematician is to prove this formalism from some particular models, which is again usually is not easy. Okay, so it's kind of first part of my lecture about different approaches and different examples and maybe ideas without full proof, without full kind of overview. So, but again, it's an old story, and basically I mentioned Mandelbrot, and there are Falconer. There are a lot of books of multifractality, and again, for instance, many papers published by French mathematician Cahan, and basically now we are going to consider one model, not all different models, in which I will try to explain how to obtain these non-trivial scaling functions and form sometimes even to prove multifractal formalism. Okay, basically this model is related to the limit theorems, but not for a sum of random variables or some stochastic processes with dependence, but for products. As I said, that it's seen from the first definition that basically multifractality can be obtained as multifractal process can be obtained as a limiting processes, but not for a sums, but for a products. From the sums, we can usually obtain self-similar objects, like Lamperti theorem gives us clear picture of self-similar objects. But for a products, and it is not like we have a product and then take logarithm of them and we have e to the power sum. It's not this process. It's a little bit more complicated object. So let me introduce this object, which is my favorite object and my area of research, in which I published several papers with co-authors about this type of object. Okay, again, our aim to prove multifractal property, to obtain some sort of non-trivial scaling functions. For instance, we already saw quadratic functions, but we would like to have other possible functions, not only quadratic, not only log normal so-called models. And again, also to keep some dependence, because for many data are independent and we could not assume independence. So this is why it's kind of models for a limiting process will be multifractal with dependence, even long range dependence sometimes. We will see this, and basically these multifractal properties. according to at least definition 2, and sometimes it's possible to prove that they're equivalent. Okay, so let us introduce some conditions. A prime is there is a lambda of t is a measurable, separable, strictly stationary positive stochastic process, and we assume that expectation is equal to 1. So we call this process mass process. So basically, inside there is a as you see, this is more or less martingale story. And to have martingale property of a product, we need this assumption that product of random variables is martingale, and if expectation is equal to 1, that's what we taught usually our students, and that's basically consequence of this. So we need this property for a future to have martingale property. And again, the second condition, we consider independent copies of this mass process, and to be rescaled by some parameter b. So basically, lambda with index b I of t in distribution is equal to lambda I t times b to the power I. This parameter is very important. We will see, and basically that's very, very important that we have here some parameter b to the power I. It's came again from idea of cascades, but formally we have independent copies f, and we have rescaled time in the following form with some parameter b. This scaling parameter b is usually larger than 1, and again we use notation that equality of finite dimensional distribution, which we already used. So basically, well, I mean, this is my favorite example when, of course, one can continue these products without exponent. But my favorite example when and most of the result I developed with my co-authors is simply when mass process is e to the power x of t. So it means that this is definitely positive process as required, and to have yes, and it is again stationary, and again suppose that there is a marginal density function pi of x and bivariate density function, and if we know, in many cases we know moment generating functions, that is clear that yes, that expectation of lambda of t is equal to 1, it simply means that moment generating function is and at 1 is equal to 1 or something. I mean, we can express all these necessary conditions in terms of the moment generating functions and bivariate moment generating functions. We assume that they exist, and then it simply means that expectation of process is equal to 1 when m of 1 is equal to 1, and variance is a finite when m of 2 minus 1 is less than 1, and covariance function can be expressed in form of the moment generating functions. That's important, that basically multifractal structure or formula we will obtain from moment generating function in this approach. Again, then we define lambda of t as a product of this rescaled independent copies of mass process. You remember that lambda b of t is we have to multiply t into b to the power I. B is less than 1. We will specify this b in the future. Not all b are good for existing of limit. And then we consider product of this object. Well, of course, we can represent it this form if you like. And then we consider the cumulative process, or maybe even measure, it's better to say. So basically, we consider A_n of t is the integral from 0 of t of the multifractal product. And you remember here there is a b, because each process is rescaled. And basically, the idea is to find a limit of such an object, and limiting process could have all necessary multifractal properties with non-trivial multifractal spectrums. So maybe it's better, yes, really to use a kind of measure, random measure. So mu n of b is integral of b of lambda s of s ds. You remember that lambda s is a product, multifractal products. So lambda n is a multifractal products here, because of a of t is integral of these multifractal products. And then basically, probably it was first Kahan who established that actually there is a almost sure limit of such an object under some conditions. However, there was no any any scenario, only existence of the limit. But anyway, it was important. Basically, that there is a L1V limit, and So I will not probably formulate properly this theorem of Kahan because we are most interested in another limits, as I said, but that's a kind of reference to the person who first considered again this object, but again, not stationary, just in form of the products. And now it's time to introduce Rényi functions, which is very close usually for many models, at least for these models, to the scaling functions of a moment. So again, let us first consider a random measure mu and interval 0, 1, and let us divide this interval into subintervals of this form, k over 2 to the power n, k plus 1 over 2 to the power n, k runs from 0 to 2 to the power n minus 1, and this is, of course, Lebesgue, so the length of this interval. Log b means log on the base b. And basically, we consider expectation of sum from k from 1 to 2 to the power n minus 1, mu, this is a random measure, you remember, to the power q of these intervals, divided log of length of these intervals and mean infimum. Basically, yes, we can write this in this form. That's what is known as Rényi function. This function is kind of related to Rényi entropy potentially, but you can see for those who are familiar with this object is some sort of, but anyway, so far we are independent. We call this function Rényi function, and in many cases, this function and scaling function of the moment is more or less the same, plus or minus 1, like Rényi functions, and that's what we will see in the future. So, at least in these models which are now under consideration. Again, so the multifractal formalism for a cascade and the multifractal process is basically, we have to consider Lejeune transform of Rényi function. You remember it was before I called for a physicist this formalism, and it was tau q plus 1. You see that basically that's exactly what this Rényi function usually is a scaling function plus or minus 1. And basically, yes, that's again, the same approach by these particular models, and yes, and that's a Hausdorff dimension of this spectrum called Singularity Spectrum. And as I said, on this spectrum we can see all dimensions. In this process is self-similar, only one point. This set consists of one point. If not, we have a, and that is why physicists can say what kind of objects they have, monofractal or multifractal. If you saw on our ads from the aircraft, you can see a lot of fractality. And the question is if this is monofractal objects, multifractal, our universe is monofractal or multifractal. That's a question of interest.
Well, excuse me, I have a question
yeah.
on the chat. So Enrique Carlos is asking, are you usually assume XT is Gaussian?
Usually assume what is Gaussian?
Some XT?
No. Yes, that's one of the assumptions we will see, but usually not. So it's important for XT is not Gaussian, and the moment generating function of XT will generate a special multifractal scenario. I will see it in a couple of minutes. You will see. No, not necessarily. Okay, Gaussian is only one example, but we are depart from Gaussianity. That's the main idea. Okay, so let me maybe omit some details, and basically we assume that B, we remember it was a scaling parameter B, is larger than 1 plus sigma square of lambda, which is variance of matter process lambda, and this is of course the same as moment generating function at 2. And then basically if if n tends to infinity, one can prove L1 conversions, and okay, let me omit. This is very difficult. That's the first results which we will generalize in the future. Some sort of difficult conditions we need to prove to be able. Basically, we assume that A of 1 belongs to LQ, which is of course very strong assumption because of A1 is a limiting process, and to prove that Q's moment exists, it's very basically that's the 19% of the theory regarding this theorem. However, if there's some very hard conditions which are initial conditions holds, basically expectation of AQ to the power Q, you remember the AQ is a limiting process of multifractal product. We are going to the limiting multifractal product, and the limiting process A of T and to the power Q behave as T to the power Q minus log with base B expectation of lambda Q of Q. You remember that lambda is a matter process of the form e to the power x of t. So basically what is written here is a moment generating function. And logarithm of moment generating function is quadratic for a Gaussian process regarding to Enrique's questions. but for a non-Gaussian, it's not quadratic, but non-linear usually. So that's why the source of non-linearity is a non-linearity of the log of moment generating functions of many processes. For a Gaussian, it's just quadratic. It's log normal scenario. So you see that, okay. So that's a key assumption, that considering mother processes E to some process with under some conditions, we can obtain scaling function, and basically that's exactly more or less Rényi function. Rényi function we have to add to this function q minus log of b e to the power lambda q of t plus or minus 1. I don't remember, but this is more or less Rényi function. Okay, again, that's a Rényi function is minus 1, is q minus 1 minus log to the power b, expectation of lambda q of t, q minus 1 minus log to the power b of moment generating function. So for a Gaussian process, moment generating function is quadratic, yes. So log of quadratic function is e to the power quadratic function, sorry, e to the power quadratic, and log of e to the power quadratic, just quadratic function. So if the process is Gaussian, we have log normal scenario because of this. This came from Gaussianity quadratic form of this log. And again, it's only L2 conversions, and basically we have to consider the intersection of the q between 1 and 2. 1 because of the result of Kahan, and 2 because of we are able to prove here L2 conversions. And again, we have to assume that A of 1 belongs to LQ is difficult to prove. So basically, it's a theorem, but we have the first our task was to kind of to present better version of the theorem, because it's very hard, and actually it's only for a q between 0 and 1, and also there are some restrictions on parameters. We have very small pieces of these non-linear functions, and simulation show, by the way, one of the papers in my list of papers is just about simulation. Actually, there's no restriction. I mean, more or less, if there is a multifractality, we have this non-linearity for many q, not only from q between 0 and 1, and maybe smaller in interval. So that's why our idea was to extend these results to, well, yes, that's exactly what I say, that usually. So what is proven that q belongs to some special sets q for which moment exists, and we have to consider intersection with 0, 1 because of only L2 conversions is proved, and from Kahan's theorem we have only L1 conversion, so that's where we are. And again, so from the martingale theory, basically we need to prove so-called LQ conversions. So basically, for any q, not for any, but for some q, and basically it means that we have to prove that that's a condition when there is a LQ convergence of martingales. Basically, this is a, well, it's difficult to prove, but formally it's clear what we have to prove to have these scenarios. Okay, so now after that, sorry, I planned this kind of series of lectures. I prepare a lot of material, but I will omit some mixing conditions because of they are kind of difficult to explain and difficult to, well, I mean, for the first lecture, it's not necessary. Yes, I will give you an example. Exactly Enrique's question. So we have a x of t is a 0 Gaussian process, and yes, we have exponent geometric version of this process, lambda of t e to the power x of t minus half of sigma square of x. It's a variance of x. So x of t is stationary, and why we need this minus? Because we need expectation of lambda of t to be equal to 1, because of we need a martingale property. So that's always we have such a procedures here. And then, of course, there is a correlation function of original process, and we can express all conditions. I mean, for a Gaussian process, moment generating function of the first order, first marginal distribution is quadratic function, but also there is a moment generating function of two-dimensional bivariate distribution. That's enough for a Gaussian processes. And basically, yes, we can express everything in terms of the moment generating functions. And as I said, that log to the power b of e to the power lambda of t to the power q, you remember that lambda of t is e to the power x of t minus sigma square over 2. X of t is a Gaussian. So log of the moment generating functions is to the power q is quadratic function. So log normal scenario, what we already called. So we have quadratic function you know, behavior of the moment, scaling of moment is quadratic here. So basically that's the exact formulation. So suppose that correlation of the Gaussian process satisfies these conditions, there are such a Gaussian processes, and if B, it's important that we have a condition on B. So you remember that go to the limit, we have to consider rescaling with time with parameter B, and B must be larger than e to the power q star sigma square over 2. So we have to consider some sort of q fixed, and then to introduce B, and then go to the limit in the multifractal product of stochastic processes. You remember that B here is to the power G, not every B, but special B, that's important. Well, there are a lot of B, but we could not do arbitrary B. And then to the end, for any q between 0 and q star, now q star is more or less arbitrary, we have a multifractal behavior, expectation of a of t to the power q is behave as t to the power minus a q square plus a plus 1 over q. Again, this is quadratic function, which we already saw in some other examples. And this is called so-called log normal scenario. Basically, the first log normal scenario was introduced by Kolmogorov in his famous 2 papers about multifractal, I forget how they called in Journal of Fluid Mechanics once, and another in another journal, but that's I mean, only 2 papers of Kolmogorov about multifractal. I mean, maybe they are not called multifractal, but basically that's a log normal scenario I introduced there in some another form, yes. Okay, and the new function is given by again quadratic function. So basically, from the data we can build analog of the. So we can estimate this moment by using method of moment, roughly speaking, and basically we can consider empirical counterpart from the data of these moments. Yes, and then we can compare just taking regression of log of this. It is called structure function sometimes, log of structure function with respect to this function. And you can estimate using least squares method, for instance, you can estimate unknown parameters here and basically to identify our model, which parameters are suitable for this type of data. Again, I'm not going to this direction because it's another direction, how to determine multifractality statistically. But what physicists do again, they use empirical counterpart of this moment, you know, and then simply compare with theoretical behavior, take log of this, and you can identify parameters via regression method, for instance. There are such paper about this, but again, it depends on the model. And okay, so again about long-range dependence. Usually, multifractality is considered on the finite intervals, and long-range dependence is a property of usually defined for infinite intervals, and basically. What is our definition? Suppose that correlation function behave a slowly varying function over tau to the power alpha, that's a stationary case. And basically, if you consider variance of this, if you can see here t to the power 2 minus alpha, and the limit exists if t tends to infinity, but formally we are not going to the limit because of our interval is finite. So that's what we called long-range dependence. So maybe it's not a good definition, but at least it's very similar. If interval would be infinity, that's exactly what one of the definition of the long-range dependence. Okay, that's explanation how this relate to the long-range dependence. That's a standard stuff for how to deal with slowly varying functions. Let me omit it, but again, that's I'm sure that long-range dependence already discussed in one of the lectures on this series of papers. I don't need this type of remark. Okay, that's example of the function for which we can log normal scenario. And again, we have dependence, even long-range dependence, we have multifractal property. Basically, that's good enough. But the only drawback of this approach is that so far we have only log normal scenario because of process is geometric Gaussian process. So the question is how to get another scenario, because for a physical point of view, there are a lot of other nonlinear functions. Not only, they are not always quadratic, and quadratic function is not, you know, it's very good for regression because of our quadratic regression. We can solve a regression equation explicitly, but in physics, there are log gamma scenarios. There are many other scenarios. That's what they discovered formally without theory. And now we are able to present at least one theory for this type of processes of observed data. Well, again, I need to define a little bit what we call Levy process and infinite divisible distributions. I'm sure that it's already discussed here in this audience. Let me not be concrete. I will assume that there is there is a infinite divisible distribution and its cumulant function and logarithm of this cumulant function. And if not, just maybe ask me, because I think that it's known that any infinite divisible random variable has so-called Levy-Hinchner representation. It means that cumulant function has this form, and there are triplet, which is A, C, D. This is Gaussian part, and this is non-Gaussian part, and nu is known as Levy measure. This is not a finite measure. Well, I assume that this is known material for this audience because of almost sure that I already mentioned this. I let you not be concrete here. But what is more important, that we consider subclass of a process is called self-similar processes, and that's a definition of self-similar processes. A random variable is self-similar, self-decomposable. A random variable is self-decomposable if for all c from 0 to 1, the characteristic function of x can be factorized as f of c times z, and some other characteristic function also depends on c. So this definition looks like a formal, but in fact, there are most of the distribution we know are self-decomposable. For instance, gamma is self-decomposable, normal inverse gamma, inverse Gaussian, variance gamma, well, in many others. In the papers I mentioned, we have a lot of so-called scenarios, maybe 10 scenarios, and they're all based on the self-decomposable distributions. Of course, normal is a partial case of this. And again, omitting some details related to this Levy-Hinchner representation, basically we need to consider so-called, this object is interesting for this audience maybe without even multifractality, simply Ornstein-Lebesgue process is driven by Levy process. So we know that if Z is a Brownian motion, this is famous Ornstein-Lebesgue process, which is Markovian, and at least under some assumptions, and basically, yes, that's a famous Ornstein-Lebesgue process. And Bartov Stinson and other, I think Wolf was the first who introduced the so-called stationary processes driven by Levy. Here, instead of Brownian motion, you consider any process lambda of t. And what is interesting is basically class of distributions, margin distribution of x of t is self-decomposable distributions. I'm not going to prove it, but there is a theory which tells us that through this construction, we can obtain any marginal distribution, any process is marginal distribution which is self-decomposed. So basically, we can construct OU process driven by special Levy process, which has a gamma distribution, inverse Gaussian distribution, normal inverse Gaussian, variance gamma. For any self-decomposable distribution, we know which Levy process we have to put to drive this equation to have to be sure that x of t has marginal self-decomposable distribution. So that is as you know that our okay, correlation function, of course, is the exponent here, and there is a relation between the cumulant function of x, which is self-decomposable, and cumulant function of Levy process z of 1. Okay, so let me omit some details which are not important for exposition. And sorry, this is a kind of prepared essay selection, but okay. So again, our idea is now to consider geometric form of process x of t, which is stationary, and driven by Levy, stationary OU process driven by Levy process. So basically, x of t has any self-decomposable distribution in this construction. And c of x, again, the constant, which means that expectation of lambda of t mass process equal to 1. So again, everything we can compute in terms of the moment generating functions if they exist, and for many cases they exist. And again, under some, yes, that's basically probably, I will almost stop here. That's yes, I mean, okay. So now it's a kind of one of the main theorem, is not main theorem, but one of the main theorem which I would like to present here. So far without long-range independence. For long-range independence, you have to go to superposition of OU processes. It's one more construction. There are literature about this, which I mentioned in my abstract. Okay, but this theorem is clear. So let x of t be OU process, stationary OU process, driven by some Levy process with Levy measure nu. Levy measure is a measure from Levy-Hinchner representation. So it means that we know that marginal distribution of x of 0 of this process, it's a stationary process, is self-decomposable, a lot of such distributions. And basically, for many distributions, we know Levy measure, like for a, for a gamma, it's e to the power minus lambda, not lambda, a b over x over x and any case. But anyway, we assume that such an integral for some q is finite. Of course, if you know Levy measure, we can check this condition very easily because it's clear what this condition is about in terms of Levy measure. And then if b is larger than this strange things, but it's very important. This condition came from in many other papers with different approaches, and analog of this condition can be observed. And basically, if b larger than some, you know that we have choose q and b larger than this quantity, which is moment generating function of our distributions of this q, and then m of 0 to the power q and to the power 1 over q star minus 1. For me, it is beautiful, but again, it's heavy, but it's possible to check, to find b of this form. Then again, such a multifractal stochastic processes, as we considered, converge in LQ sense, not in L2 or L1, but LQ sense for this special Q, which is already chosen. And process AT, limiting process, belongs to the LQ. And the scaling moment of this process behave as t to the power q minus log to the power b, e to the power lambda q of q. You remember that lambda of q is e to the power on a Steinberg process. So log of the moment generating function is nonlinear for a gamma distribution, for a inverse gamma distribution, for a normal inverse Gaussian. So we can obtain nonlinear behavior of our moments from this, from using practically, well, of course, we have to check some conditional Levy measure on B, but potentially we can obtain from any self-decomposable distributions, for most of them nice distributions, we can obtain nonlinear behavior of the scaling function or NE function, if you like, from this theorem. Because of, again, lambda of t is e to the power x of t minus some constant. X of t has self-decomposable distribution like gamma, normal inverse gamma, variance gamma. So log of, well, okay, to the power q, it means that we have simply to multiply under the exponent some expression into q. And basically, yes, log of this function is the definite nonlinear function for majority of self-decomposable distributions. Probably it's linear only for a, I even don't know if there is a, probably there is no any case when it's a linear function. And this is kind of one of the results in which we can obtain multifractality as a limit of multifractal processes with some dependence. It's still not strong dependence. To go to long range dependence, we have to consider not on Steinberg process, but so-called superposition of AU processes. And via this methodology, one can obtain this type of results. So maybe I will give one example of this function, but again, I have to skip a lot of, well, basically that's a Rényi function. You can see that, yes, the Rényi function is a log of moment generating function. Moment generating function from any distribution is nonlinear. So log of this is e to the power, maybe something else, but it's a source of nonlinearity with respect to q because of the first part is linear one, and the source of nonlinearity is the second part. Okay, maybe I will find one more example how this function looks like for okay, that's about how you obtain, I mean, all the superposition, and that's yeah, how to introduce long range dependence, but okay, yes. Just one example of scenario which you can see what is here is a log temporary stable. Oh, okay, it's complicated, but anyways, that's okay. That's okay. It's complicated, but I mean too many parameters here. Okay, so we know the temporary stable distribution, which is almost very popular among the people who study fractional calculus because there is a stable, temperate stable, and again, what is important that okay, that's the density and sorry. Yes, I mean, log of moment generating function of this so-called temporary stable distribution is given by this formula. Okay, zeta is a parameter of the moment generating functions, and you can see that it's completely nonlinear. Yes, if kappa is equal half, this is inverse Gaussian distribution. There are more simple. So basically, that's a log of moment generating functions, and basically we can see these functions now. If you consider that this distribution is self-decomposable, so we can create yes, the Levy measures of the distributions, and we can check all conditions about Levy measures of Levy process, the process itself, everything is computable here. And to the end, yes, we consider the mother process as e to the power x of t minus s of x, c of x. X of t is a OU process with marginal distribution, which is temperate stable. Okay, C of X just to have expectations equal to 1. And, oh, sorry, what's, sorry, it's oh, it's already superposition. Oh, sorry, that's okay. Okay, that's a typical result. So, okay, basically, okay, that's when so-called log inverse Gaussian, when one of parameters is equal to half. So, and in this case, that's a temporal stable when one of log parameters is equal to half. So you can see that a renew function is given by Q times some, depends on parameter of the distribution, delta, gamma, B, yes. But this is of course linear part. But after that, there is completely non-linear part. That's a case when we have log inverse Gaussian scenario, so-called, and some other function. So you can see this linear part is not quadratic, and well, it's square root of gamma square minus 2q. And it holds for any q of special form, unfortunately or fortunately, because it depends on parameter. And B is, when we use model simulation, we have to choose B of very special case. You see, even in here, B is complicated. However, it's given explicitly. So for all interval between 0, first of all, we have to choose Q. And then for this Q, we have to choose B. And then to create multifractal scenario. And in all papers which are mentioned, there are a lot of examples of such a scenarios, like 6, 5, 7 without long range dependence, with long range dependence. So let me stop here because of my time is over. Well, again, sorry for the style, because actually the third part was expected to be a subject of several lectures, which I plan to do in Brunel, and but unfortunately now life is different, and yes, that's only one lecture. But again, all slides are available, and all literature are in my list of, after abstract, there is a list of, I think I mentioned all papers, or maybe some of them. But anyway, thank you very much. That's the end. Let me stop here. So again, for many self-decomposable distributions, such as inverse Gaussian, we can construct on Steinberg process driven by special Levy process to be sure that that's a margin distribution inverse Gaussian. Then we can consider the mother process, which is e to the power geometric form of this OU process driven by Levy noise. And then we have to consider this multifractal product, which I already introduced several times, even product of such a processes, in which time is rescaled by some parameter B. And the special choice of B, the limiting process is multifractal. And in this case, it has dependent but weak dependence, but in other cases, it could have even strong dependence. And this is true for interval Q between 0 and some part depends on the parameter of the inverse Gaussian distribution, but some also from Q star. Again, unfortunately, negative Q is not mentioned here, but again, it's an open problem to prove similar result for a negative Q, because for application, negative Q has special interest. Sorry. Okay, that's all. Thank you, Elena.
Yes, thank you very much, Nikolai, for interesting and very intense lecture. Thank you. I wonder if there are any questions. Yes, I can already. So Enrique Scala is asking, are there any news on the equivalence of the different definitions of multifractality? Is there a general framework?
Yes, I mean, well, in general framework, this paper with my PhD student Grahovac from Croatia, we try to collect all definitions and all cases when there is equivalence. And we submitted this paper about 30 pages to journal Fractals, and then the referee asked us to make sure that the first part in which it was equivalent. So now this paper is published in Fractals, and of course not in full form, unfortunately or fortunately, I don't know. It was wishes of referee, but however, I have a full copy of this paper, not published, but which was submitted originally. And in this copy, for those who are interested, just send me an email. There is all information I know about equivalence, when these conditions are equivalent. All examples are mentioned in this paper. According to our investigation, maybe there are people who investigated this object better, but what? Yes, that's according to our investigation. Of course, this is a very, very long story. And for those who are interested, I can send them just a manuscript, of course. But again, part of this paper, maybe 90% or 75% of the paper is published in Fractals and available. But another part was simply omitted because of the referee asked us to cut, as it's often happened. And in a sense, he or she is true, because she was right, because actually it was not our results. We collected these results from different sources, and not even that's my answer. So. But again, it's very difficult to find models in which all three, even two definitions are equivalent. For instance, for a cascade, it's true. And for a cascade, multiplicative cascade, even formalism is proven completely. But I'm afraid it's very rare in situation when we can prove equivalence of all three definitions and to confirm that multifractal formalism works. That's very rare, but sometimes possible. But what is more often that we can prove multifractality according to one of this definition, and to prove the correctness of the multifractal formalism. That's more easy in a sense.
Thank you very much. There is another question. Can you say a bit more about the sense in which linear fractional stable motion appears to be multifractal? It has a single H that depends on parameters.
Yes, linear stable motion is monofractal because of its self-similar. So, and in this sense, spectrum of singularity is equal to 1 over H. 1 over H over alpha as far as, so there are two parameters. One is parameter of self-similarity, H, and another parameter of the tails, as far as I remember, alpha. So basically, there is one of my paper in Journal of Statistical Physics I mentioned in abstract. It is the co-authors, the Grahovac, my PhD student Murat Taku from Boston University, and me. And this case is considered in all details, what is called stable motion. And actually for this case, so in this paper, okay, there are a lot of papers even, but what we did in this paper, we simply, so there is a some approach. What we can say using multifractal approaches to monofractal objects. Actually, we can do a lot with these approaches. That's another part of the last part of my lecture. So basically, all this idea of multifractality can be applied for a monofractal object. Basically, we can estimate parameters. For instance, for a stable motion, we can estimate both parameters: parameter of dependence H and alpha, parameter of tail A. We can see geometrically from multifractal functions, objects are monofractal, as I said. But we can apply multifractal analysis. We can try to build scaling function to compare with empirical functions. And in this paper, we did it for a simulated data and even for a real data. So that is why it's possible. Also, maybe, so let me go to the end. I will show you how to apply multifractal, monofractal objects to, okay. So how to apply multifractal ideas to monofractal objects? Okay, that's basically what we called partition function, which is empirical counterpart of the Q's moment, which we are using scaling functions. And we can scale this empirical scaling function. And basically, yes, we can see estimate parameters using sorry, just. I see how to estimate parameters of, yes, okay, that's a, okay, partition function is analog of the Q's order moment, basically. That's the empirical counterpart of the left-hand side of our multifractal analysis. Again, this is for monofractal objects. Taking some logs, taking some computations, and to the end, we can see all parameters of the model in behavior of this function. I will show them. Oh, yes, that's one, okay. So for instance, suppose that you have a student distribution, yes, or heavy-tailed, any failed-tailed distribution, stable parameter alpha. You see the stable parameter alpha is here simply. Because of this is multifractal empirical scaling functions, let's say, and we can see scaling parameter here. For instance, this case is equal to half or one, I don't know, yes. So that's, I think, for a student. I forget the examples, but okay. And there are many such other examples. Sorry, only one. Yes, I mean maybe it was before. So this is kind of my last. I plan to give several lectures, and this my last lecture. But anyway, again, that's I invite you to try to apply it multi. Oh, there is only one picture again. So again, there is a suppose that we have a on-Steinbeck process with student margin distribution. Student is cell decomposable. Such an on-Steinbeck process exists. Yes, heavy tailed. You have to estimate this parameter alpha, parameter of tails. So you can see simply plot the scaling functions. And you can see the scale parameter is simply here. So if model is monofractal, like normal, if not heavy tailed, we have just a line. But if heavy tailed, we have how heavy is a V, you can see from multifractal spectrum. So that's how to apply the idea of multifractal analysis to monofractal objects because of stable, what is called stable motion, what is called linear stable motion. Yes, linear stable motion is monofractal process, is self-similar, and we can estimate both parameters, heavy tail of this alpha and h, which is related to long-range dependence from this scaling function. And this paper is published in Journal of Statistical Physics. It's Murat Taku, me, and Daniel Grahovac. So that's probably all, because otherwise he has a reason about this, but of course I have no time to go to details.
Thank you.
And again, if somebody likes to see the some of my papers, just send me a mail, and all papers are available. I can send all. I would be happy to send my research papers, published research paper to people who are interested in. Okay, so part of mathematics. And basically, we can see multifractality from aircrafts. Probably all our world is more or less multifractal. Of course, we can simplify it to monofractal objects sometimes, like fractional motion or stable or linear stable motion. But even for a monofractal object, if you will apply multifractal ideas, like all the scaling functions, you can see a lot, because of many scaling functions behave like here bilinear, and you can see geometrically all parameters in these pictures. And from this geometrical picture, you can estimate parameters. Basically, it's a little bit, Actually, this paper is with estimation of 2 parameters using idea of multifractal analysis by using for a linear stable motion was generalized by Mark Podolsky from Aarhus University, and his some PhD students. Now it's published in, I saw today even this paper published in Statistical Inference for Stochastic Processes. And basically, they developed our methods to the confidence interval. So because our method is more or less kind of empirical, you have to see parameters here, how to see parameters here by eye, but they developed this method to the kind of logical story when we have confidence intervals and so on. And today I've got via email confirmation. Well, I mean, usually when paper is mentioned, you got through email information that your paper is mentioned some paper. Today, just opened and saw this type of generalization. Okay, other questions? So,
are there any questions? Well, then, thank you again for very interesting talk. And well, indeed, if you think of a question, you can email.
Yes, and all slides in full. There are how many slides? 166, and I performed only, I think, something like 30. I don't remember how much. It already was heavy, but of course, I need more time simply. But all slides are available on the page, and all papers are published. I mean, there is no secrets here. Yeah.
Well, I hope. Well, we probably could invite you sometime. To spend more time.
Yes, interesting to think about financial data. If they are monofractal or multifractal. About this also, I plan to say something, but not now. Next time, yes.
But I guess we should stop now, and you have your other responsibilities to go.
Yes, I have another meeting. You are right, absolutely.
Yeah. So thank you very much again. Yeah.
And thank you for listening.
Yes, and I would like to announce that today there are exercises at 3:30, and those of you who are attending the sessions, you can stay here or just log in just before 3:30. And as yesterday, it will be done in the same format. The solutions for the yesterday sessions are already on the website. So thank you, and
thank you. Have a good day, and thank you again. Bye.
Thank you. Bye-bye. Bye.
Thank you very much. Bye.